So, Chapter 9 is all about magnetism and something related to magnetism called electromagnetic induction that we're going to learn about later on. But we're going to focus on the idea of magnetism because magnetism is something that people are familiar with, but they don't often really deeply understand it. And so we want to give you a better understanding of some of these ideas. Also, we should note that magnetism and electricity are intimately related to one another. They're very closely tied together. Now, we're going to start out by talking about bar magnets. You're probably familiar with different kinds of physical magnets like that. So, you may have some magnets on your refrigerator holding up your kid's artwork, or maybe your parents did that when you were a kid. And you may have seen different types of bar magnets. So here on the left, we can see a bar magnet, and you can see that it has labeled its two magnetic poles, the North Pole and the South Pole. All magnets have two poles, and they're named the North Pole and the South Pole. And you learned the basic rules about them in grade school, probably. You know that like poles repel one another. So if you have two North Poles or two South Poles, they're going to repel one another. And opposite poles attract one another. That is very much like how charges behave. Remember, we talked about how with charges, if you have the same kind of charge, either two positives or two negatives, they repel one another. But if you have two opposite charges, a positive and a negative, they attract one another. It's the same thing with poles. And you might also look at this image of this magnet here. You can see that it's showing magnetic field lines. Now, we talked about electric field lines in the electricity chapter. Magnetic field lines work the same way as electric field lines, but they obviously deal with magnetism rather than electricity. And if you're looking at this pattern of the field lines surrounding this bar magnet, you may think that it looks a little familiar. And in fact, it looks exactly like the field lines from an electric dipole. Remember, if you have a positive charge and a negative charge, the field lines look kind of like this. You can kind of see it's the same kind of pattern. It's because we have two different opposite charges. Well, here in the magnet, we have two different quote-unquote opposite poles, a north and a south. And the field lines go from north to south, and they follow the same pattern as a dipole if you have a bar magnet, because it's another kind of dipole. Remember, dipole means two poles. And so we have a north pole and a south pole in the electromagnetic field lines. Now, you may also have seen in cartoons, and you may have even seen one in real life, a horseshoe magnet. It's a magnet that's bent around, shaped kind of like a horseshoe. And the ends of the horseshoe magnet behave the same way. And so you have a north pole and a south pole. You can get the same kind of magnetic field lines going between them. So the takeaway from this slide is this. Every magnet has two poles, a north pole and a south pole. The field lines go from north to south. And if you have a bar magnet, the field lines look just like an electric dipole where you have a positive charge and a negative charge, only here you have a north pole and a south pole. Now here's a picture of an actual bar magnet, and its north pole and its south pole have been labeled. And then what someone did was they sprinkled some iron filings, little teeny tiny pieces of iron, almost like iron dust. And what happens is those little slivers of iron, they behave like compass needles, and they line up with the magnetic fields. And so what you can see is you can see those kinds of field lines. You remember in the last slide we showed how the field lines kind of curve up and curve back down. You can kind of see that as these iron filings have lined up like little compass needles, and that's a way of actually demonstrating the direction of the magnetic fields. So why do compass needles line up with the magnetic field lines? They line up along the field lines to point in the north and south direction, but why is that? Well, generally, the compass needles themselves are little magnets. Now, they may be permanent magnets, or they may be something like a piece of iron filing that's temporarily magnetized by being put in a magnetic field. But either way, the little pieces of iron are effectively magnets, and so when you put them in a magnetic field, remember, the magnetic field is showing the direction of the magnetic force from the North Pole to the South Pole. And so if you had a needle that's actually a little bar magnet, so this might be the South Pole and this might be the North Pole. Well, the South Pole is going to be attracted to the North Pole, and that's going to create an upward force here. The North Pole is going to be attracted to the South Pole of the magnetic field, and those two forces together are going to pull this needle and make it rotate. Now, it may be hard to see here, but there's actually sort of a pin right in the middle, and it's able to rotate around that pin. So the needle will be pushed up and pulled down so that it lines up with the magnetic field. And you can see that in the right, where these forces have pulled this guy up and pulled that guy down, creating a twisting force. We call that a torque. It creates a torque to rotate this guy so that it lines up with the field. So the next question is, if I have a bar magnet like this and I break it in half, what happens? The answer is I get two bar magnets. So this bar magnet in its original form has a North Pole and a South Pole. Now there's a kind of a rule in nature that you can't have one without the other. I can have, in electricity, I can have a positive charge without a negative charge, and I can have a negative charge without a positive charge. But in magnetism, the two different poles are tied together. If I take this bar magnet and I cut it in half, you might guess, and this would be the wrong guess, by the way, but you might guess that you'd have the North Pole and the South Pole and they'd be split. But what actually happens when you cut it in half is a new South Pole will form here and a new North Pole will form here, and now you've got two smaller magnets, each with their own North and South Pole. And no matter how many times you cut the bar in half, that process will keep repeating. If you have a North Pole, there has to be a South Pole that goes with it. That's the rule. And so the answer is, can you have a single pole by itself? You never can. It's not possible. The next thing that we want to talk about is something called magnetic domains. And I'm going to look over here at this, over on the right first, where I've got this bar of iron, and at first it's unmagnetized. Now, if you could zoom in microscopically and look at the structure of this unmagnetized iron, you'd find that there were like little bitty clumps of iron, that each little clump of iron was behaving like its own little tiny magnet. But these little tiny magnets would be randomly oriented. So for example, you can see right here, there's a little one that's kind of sort of pointing to the left, and here's one that's kind of sort of pointing to the right. Those two guys would more or less cancel one another. And here you have one pointing up, and here you have one pointing down. Those two guys would more or less cancel each other. And so while if you were looking at the microscopic level, you'd find lots of little magnetic fields being generated by these little lumps, each one acting like its own magnet, the total magnetic field of the bar would be zero. They'd all cancel each other out. But if you put this bar of iron into an external magnetic field, a magnetic field made by something else, what you'd find is that these little lumps, we call these little lumps magnetic domains. They're like little tiny magnets inside the iron. They'd start to line up with the magnetic field, just like the iron filings did when we dumped them around the magnet in one of the previous slides. And so if you put it in a weaker magnetic field, you'd get this guy would become slightly magnetized. And if you crank up the magnetic field, they would become more strongly magnetized. Now here's the thing. If you take away that external magnetic field, this guy will demagnetize itself and go back to being in the unmagnetized state. So that's why every lump of iron in the world isn't a magnet unless you stick it in a magnetic field. Now, here's the cool thing though. If you take this guy and you heat it up really, really hot and put it in a strong magnetic field to get all these magnetic domains lined up, and then you cool it very, very slowly, you can leave it so that all the domains are permanently lined up. then you have a bar of iron that has become permanently magnetized. Not just strongly magnetized, but in that case it would be permanently magnetized. Now, if you have a strongly magnetized bar and you cut it in half, guess what? You still get a south pole and a north pole. And you can kind of see why that is, because these little microscopic domains, each one is like a little tiny magnet on its own. And so it's going to have its own north pole and its own little south pole. You can see the same thing here. So if I cut this guy in half, if I look at the domains, they're all stacked together. So I've got south, north, south, north, south, north. And so I'd have a north pole over here, and I'd have a south pole over there. It's kind of how that works. And so the figure over here is showing you sort of that microscopic view. And I was calling them little lumps of iron. They're actually what we call crystals. It's a crystalline structure. And these little magnetic domains exist within these crystalline structures. And if you put them in a strong magnetic field, they'll line up just like we were talking about. But if you don't have a magnetic field and it hasn't already been magnetized, these magnetic field domains are the north and the south are going to point in random directions, and they'll all cancel out. By the way, not every material can do this. In fact, most materials can't. Iron is one of the very few materials in nature that can be magnetized like this. One of the things that a lot of scientists have spent a lot of effort on over the years is finding different chemical compounds that are capable of being magnetized in the same way that iron can, and they've learned how to put those compounds together. But of the pure elements, the ones in the periodic table, there are only 3 out of the 120-ish elements that exist. Only 3 of them are able to be magnetized, and of them, iron is by far the best at it. So a lot of magnets are made out of iron for that very reason. But if you need really, really strong magnets, then you can use some of these other materials that scientists have figured out. So let's look at our checkpoint to test our understanding. Question number 1, why doesn't a magnet pick up a penny or a piece of wood? If I had a bunch of iron filings and I scattered them on the paper and I brought a magnet near them, the iron filings would be attracted to the magnet, and you could actually lift them off the table and they'd stick to the magnet. You can't do that with shavings of wood or with pieces of a penny. Why not? Well, it's just what I was talking about. Not every material can be magnetized, and iron is one of those special materials that can. But wood and copper, which is what pennies are made out of, and actually zinc is what pennies are mostly made out of, but those materials can't be magnetized. So if you bring a magnet near them, they're going to ignore that magnet. They're not going to be attracted. They're not going to be repelled. They're just going to sit there. So the next question is, how can a magnet attract a piece of iron that's not magnetized? And it's just like I was saying, when you have a piece of iron and you put it in a magnetic field, it's going to temporarily magnetize it by lining up those domains. And so then that normally unmagnetized piece of iron will behave like a magnet and be attracted or repelled to the poles of your actual magnet. Now you take your actual magnet away, that piece of iron is going to go back to being just a normal piece of iron that is not magnetized. So what is it that makes magnetic fields in the first place? How are magnetic fields created? And the answer is very simple. Magnetic fields are created by electric currents, by flowing charges. Charges are moving, magnetic fields get created. That's just how it works. Now, it's interesting, if you have a straight wire that's carrying a current, so you can see up here I've got a straight wire that's carrying a current, the magnetic field will actually form as loops surrounding the wire. And you can kind of see that in this figure on the right. We've got a wire that's going straight up and down, and it's piercing through a piece of cardboard on which we've laid a bunch of compasses in a ring. And what will happen is the magnetic field around that wire is going to be a loop, and those compass needles will all line up with those magnetic field lines. And so you'll see the needles pointing in a circle around that wire. it's a magnetic field line that loops around the wire. And of course, we can see that over here as well. We have a straight wire, and those magnetic field lines are loops around it. Now, the lower picture is kind of interesting. We have the wire, and we've bent the wire itself into a loop. And the question is, how does the magnetic field lines look for that looping part? And you can see there's still, the blue part represents the magnetic field lines, and there's still loops all around the wire. Now, this is an interesting picture because if you remember, I showed you just a bit ago, if I have iron filings and I dump them over a bar magnet, they're going to line up with the magnetic fields. The same thing will happen if I have a current traveling down a wire. Remember, currents or moving charges make magnetic fields. And so here I've got a wire piercing through a piece of cardboard just like in the previous slide, and if I dump a bunch of iron filings on that cardboard, you can see that they are lining up in circles around the wire, showing that the magnetic fields are represented by different loops. And if you look at the magnetic field lines around a loop, you can see that they're coming kind of straight up and down through the loop itself, but making circles around the wire all around. That's kind of cool, right? And you can see the same thing with multiple loops. You can see that inside the loops, the magnetic field lines are very straight, but around the edges of the loops, they're kind of looping around. And this coil of loops here, the magnetic fields are actually behaving almost like a bar magnet, which is kind of neat. Now, one thing you might ask yourself, where's the current in a bar magnet? Because I said just a second ago that all magnetic fields are created by moving charges. And so I've got a north-south pole and a bar magnet. Where are the electric currents? Well, if you zoom in, you know that the bar of iron is made out of atoms, which have protons and neutrons in the nucleus and electrons spinning around them. Those electrons moving around the atoms are moving charges. And so every atom has its own little bitty magnetic field. Now, the thing about iron that's special is that all of those magnetic fields of those individual atoms can line up and form those domains like we were talking about. That doesn't happen with something like gold or copper, but with iron it can. And so, but the source of the magnetic field, even in a bar magnet, is still a current. It just happens to be the current of the electron spinning around its own atom. Of course, the magnetic field around every individual atom is very tiny, but in something like a bar of iron, you have a whole lot of atoms, and so all those tiny little magnetic fields add up to something much bigger. But of course, that can only happen because iron lets those little magnetic fields line up together. Something like copper is not going to happen.